before, making me stronger, taking me right to the core. Oh, I don't know in the start, never heard it from above. The world isn't hard, but I know in my heart, if you ain't mine, I'll be torn apart. I don't know who's gonna kiss you when I'm gone. So I'm gonna love you now, like it's all I have. I know it'll kill me when it's over. I don't wanna think about it. I want you to love me now. I don't know who's gonna kiss you when I'm gone. So I'm gonna love you now, like it's all I have. I know it'll kill me when it's over. Don't wanna think about it. I want you to love me now. You to love me now. Something inside us knows there's nothing guaranteed. Yeah, and girl, I don't need you to tell me that you never leave. Lord, when we done something that we could to turn darkness into light, turn evil to good, even when it's too hard. For that perfect kind of love, it could fall apart. And gonna kiss you when I'm gone. Oh, I'm gonna love you now, like it's all I have. And I know it'll kill me when it's over. I don't wanna think about it. I want you to love me now. Oh, love me now. Oh, love me. Don't go down. It's alright. Let's make free tonight. I don't know who's gonna kiss you when I'm gone. So I'm gonna love you now, like it's all I have. I know it'll kill me when it's over. I don't wanna think about it. I want you to love me now. I don't know who's gonna kiss you when I'm gone. So I'm gonna love you now, like it's all I know it'll kill me when it's over. Don't wanna think about it. I just wanna love you now. Oh, yeah. Oh, love you now. Oh, you now. Oh, if I
To understand what an eclipse is, we have to look at our solar system. At the center is our sun. Our sun is a star, just like the ones we see in the night sky. There are planets circling a lot of those stars too, but that's another story. The sun is the biggest, most massive object in our solar system. It's a huge source of light and heat and has a strong gravitational pull. This helps keep all of the planets in orbit. An orbit is a curved path of a celestial object around another object. So planets orbit the sun. But there are other things that orbit the planets too. These are called moons. The Earth has one moon, but other planets have way more. Jupiter, for example, has at least 95 moons. We may not notice that we're constantly in motion, but we can tell by the way the sun moves in the sky and how the environment changes around us over the course of a year. Actually, we're on quite a ride. The Earth orbits around the sun at a speed of 67,100 miles per hour. That's the equivalent of traveling from London to New York in about 3 minutes. So, planets orbit around suns, and moons orbit around planets. Sometimes these celestial bodies block out the sun's light and cast shadows on one another. This is an eclipse. On Earth, we observe two main types of eclipses, lunar and solar. In the case of a lunar eclipse, the light from the sun, which usually bounces or reflects off the moon, is blocked out by the Earth itself. The Earth gets in between the sun and the moon. Solar eclipses occur when the moon blocks out the light from the sun. So the moon gets in between the sun and the Earth. Although the moon is much smaller than the sun, the moon is also much closer. The diameter of the moon is roughly 400 times smaller than the sun. But by amazing coincidence, it also happens to be about 400 times closer to the Earth. So, during a total solar eclipse, the two bodies are at just the right distances to make them appear to be the same size in our sky, like a cosmic optical illusion. Not every solar eclipse is a total solar eclipse. During a solar eclipse, the moon passes between the Earth and the sun and blocks all or part of the sun. The moon's orbit around the Earth is not quite circular. At times, it's closer to us than others. As a result, the moon's apparent size changes over time. We call the moon's closest point to Earth perigee, and its farthest point from Earth is apogee. During a total solar eclipse, the moon lines up perfectly, fully blocking out the sun while near perigee. In a partial solar eclipse, the moon only blocks out part of the sun. And during an annular eclipse, the moon is near apogee, too far away from the Earth to completely block out the sun, but you still see a ring of light in the sky. Two shadows are cast during an eclipse. The first is called the umbra. It's the dark center of the eclipse shadow. It's the part of the shadow where all light is blocked. The larger partial shadow is called the penumbra. While the Earth rotates or spins on its axis, the moon's shadow travels along a path spanning hundreds of miles on the Earth's surface. The path of the moon's shadow is called the path of totality. During the eclipse, anyone within the path of totality will experience darkness for a few minutes while in the moon's umbral shadow. The closer you are to the center line of the umbra's path, the longer totality lasts. Weather permitting, people along the path of totality will see the sun's corona, or outer atmosphere, which is usually obscured by the bright face of the sun. Those outside
NASA is going back to the moon.
Still worth experiencing. For 3.5 minutes in the middle of the day, the sky will darken as if it were dawn or dusk. The temperature will drop, and you may even notice animals behaving differently. An eclipse is something you won't want to miss, but you must observe them safely. You never want to look directly at the sun, especially not at a solar eclipse. Protect your eyes at all times.
NASA is going back to the moon, joining forces with international partners. NASA is leading the partnership alternate and it is first space station in lunar orbit. NASA is going back to the moon, joining forces.
Mic check 1, 2, 3, 4, 5, 6, 7, 8. Mic check 1, 2.
But give you the power to be. First of all, I won't take you cheating on me. Tell me, can I trust if I can't trust in you? Can I refuse to let you play me for a fool? Yeah, yeah. That's what you told me. That's what you said. have it all. But first there are some things you know. You wanna live with all I have to give. I need to feel true love. Gotta do it again. Would you do, baby? Tell me right to be untrue to your style. Baby, you gotta be you. Can't feel like you. But would you be, baby? It's time. I'll be like, to be untrue to you gotta be. That's not a me, baby. Mm, yeah. Oh, na na na. If you had died, I gave you all. Would you comfort me? Birthday. Time. It's the question of what victory. You, I have to tell someone it's nothing new, but I still can handle it. That's why I'm giving you a clear, ready, a hard day. It's just not fast queen. That's why I'm giving you a train ready, a hard day. It's just a nothing fast queen.
Good afternoon. How's everybody doing this afternoon? Everybody having fun at Eclipse Palooza? Everybody excited for Monday? Everybody get your big fans ready to blow those clouds away, right? We don't want any of that. Well, we're excited that you're all here today. We're also excited to have our NASA subject matter expert series. And the next up in this afternoon's expert series is Bianca Rhym. And Bianca joins us today from NASA's John F. Kennedy Space Center. And currently, she's serving as the Research and Technology Studies Manager for Gateway Deep Space Logistics. Bianca is orchestrating a symphony of innovation propelling humanity toward the lunar vicinity and beyond. The Gateway will be an outpost orbiting the moon that provides vital support for human explorers on the lunar vicinity, as well as a staging point for deep space exploration. It's a critical component of NASA's Artemis campaign, a NASA-led collaborative effort with commercial and international partners to return humanity to the lunar surface and establish the first long-term presence on the moon. Bianca's contributions to the Kennedy Space Center span across the spaceport, ground systems, operations, research, and technology projects, and into the galaxy. With her curiosity, passion for exploration, and drive to push the boundaries of human endeavor from logistics to lunar landings to aspiration for Mars, Bianca is a key player in enabling humanity to boldly go where no one has gone before. Love that quote, right? And having the time of her life while doing it. Please join me in welcoming Bianca Rhym. Sorry.
Okay. Hey, good afternoon, everybody. Thank you. Is this mic on too? Okay. I would think I was getting a little interference there. But thanks everybody for coming out today. As Troy said, I'm with Gateway Deep Space Logistics. I'm the Research and Technology Studies Manager. And I'm going to start by telling you a little bit about Gateway, or letting the experts at explaining Gateway tell you a little bit about Gateway with a video.
NASA is going back to the moon. Joining forces with international partners, NASA is leading the partnership of building Cosmic Gateway, humanity's first space station in lunar orbit.
So that's a little bit about Gateway. I'm going to tell you a little bit about deep space logistics, kind of the evolution of deep space supply chain, and then we'll talk a little bit more about Gateway and the solar energy and how eclipses actually affect spacecraft that are in orbit, and some unique things about Gateway, how we picked an orbit to avoid eclipses. So we're going to put a lot of things together, but hopefully at the end, some of the things that you hear people talk about when they're talking about space exploration and they seem complicated or, like rocket science, that they'll feel pretty natural to you and easy to understand. Sorry, I'm going to turn this off. Okay, I think that's going to be a little bit better. So let's start here. Deep space logistics, what we're doing is building a deep space supply chain. And that's kind of like you see trucks going all around the country, bringing cargo, from one part of the country to another part of the country and getting it into warehouses and then to stores. Well, we want to do that, but we're going to do it in space. So we have to collect all of our supplies from locations that are around different locations on the Earth. And then we have special packaging and preparation and processing facilities that will then take them and integrate them into spacecraft, transport them to locations in space. And some of those will be orbiting the moon, some of them will be the lunar surface. Hopefully, one day we'll get them to Mars. So that's kind of what we'll do. And then we have to also look at storing, maintaining, and returning some of those things back to Earth. So that's kind of like our full circle supply chain. If we look at the evolution of that, back in the Apollo era, we started with really launching from one location on Earth, going 250,000 miles to the moon, kind of doing a little, overnight trip or something like that, kind of just a short-term stay, collecting samples, doing science, and then bringing that stuff back in the Apollo capsule. Moving into the ISS era, the International Space Station era, we have launches from not just two, but I think three locations on Earth, actually. And really only going about 250 miles off of the surface of the Earth to the International Space Station. But we established a really regular cadence of launching and returning cargo and people. So it's a good evolution because it proves that we can have a permanent presence in space of humans. And then in the Artemis era, what we're looking to do is expand those operations to launch from many locations on Earth. We'll go to the lunar vicinity, so we'll have an orbital outpost, the gateway. So we'll send cargo and people there. And then we'll also take them to the lunar surface and hopefully extend that even further from that 250,000 miles out to almost 150 million miles on the Martian surface. So really kind of puts together all of that heritage. And we're going to kind of leverage and take advantage of everything we've learned along the way to do things better and smarter. So just kind of looking at where we got a lot of our experience from, the International Space Station, I want to kind of make a little comparison between Gateway and the International Space Station. So if we look at the International Space Station, in terms of volume, we look at it like kind of like a 6-bedroom house, holds 12 people, it's crewed 365 days a year, and it's pretty heavy. We have 420,000 kilograms of mass. If we look at Gateway, we could look at that more like a 2-bedroom condo. Holds about 4 people. It'll only be crewed for about 30 days per year and about 63,000 kilograms of mass. So really downsizing. Some of that represents kind of advances in technology that allow us to do things kind of in a smaller footprint, but also the fact that really we want to kind of limit that mass because mass is one of the big drivers of things of cost. So when Gateway is put together, we'll kind of start by launching what you see here, the Habitation and Logistics Outpost. We call that HALO, and the Power and Propulsion Element. We call that PPE. So those two pieces of the Gateway will launch together on that SpaceX Falcon Heavy rocket that you see on the left, and they'll go and they'll start orbiting. We have a lot of other components that are kind of like visiting vehicles, and also other permanent elements like the international habitat that we call IHAB, the Gateway External Robotic System, the Canadarm, which is kind of something that we see on the International Space Station as well. And then we have like human landing system, the logistics module, Orion. Those are going to be visiting vehicles that will come in and out depending on Artemis missions, because when we want to make sure that we have all of our cargo and supplies ready for the crew when they come. And we want to have our human landing system docked and ready, landed at the Gateway before the crew gets there. And the last thing that will happen is that the crew will come in the Orion capsule and they'll get all the cargo and everything that they need into the human landing system and transfer themselves into the human landing system so that they can go down to the lunar surface and conduct their experiments and start to develop that permanent kind of base camp on the moon. We also have a logistics module that's being developed by the Japanese Space Agency. And I really highlight all of that because you see all of these different companies and countries that are participating. And so this is really an international collaboration that we're developing. So early gateway science, well, really gateway science will focus on earth science, study of stars like heliophysics and the sun, lunar and planetary science, life sciences, astrophysics, fundamental physics. So, a lot of times people ask, like, why do we even go to space? Why are we doing this? We do this a lot to study the Earth, and we also do it to learn more about the universe. So, these are just a few of the things that we'll learn when we actually start conducting experiments on Gateway and the lunar surface. The early gateway science will focus on really the sun and radiation and its effects on people, equipment, and the earth. So, in that, again, International Space Station on the left orbiting the Earth, about 250 miles from the Earth's surface. Gateway is about 250,000 miles away from the Earth and will orbit the moon and have really good views of the Earth and the sun so that they can make observations and get some science investigations going. So I want to talk a little bit about the solar arrays. That is how the Gateway and the International Space Station are powered. They're both powered by solar energy. So I want to show you a little bit about the solar arrays that are on the International Space Station and then how they're actually evolved to power the Gateway.
Sensitive section. The International Space Station has been powered by large, heavy, and complex electric forces, but it's expected these drives to dissipate over time. Let's do an experiment with flashes from an abnormal food levels.
So those solar arrays are pretty cool. They roll out like a yoga mat, and they're actually able to collect more power than the previous version of the solar arrays. So the gateway version of the iROSA will actually be installed on the power and propulsion element that we call the PPE. So obviously there's power and there's propulsion. So those are the two kind of functions that the PPE serves. As far as power goes, the solar arrays generate about 60 kilowatts of power. They're distributed throughout the power and propulsion element as well as to other gateway elements. So, we talked about the iHab, the visiting vehicles. Those are all able to draw power from the gateway's power and propulsion element as they connect and dock through the docking port. The power will get distributed not just to the elements, but also to other equipment that needs the solar arrays and needs power, like the external robotic system that we talked about. That will be able to be powered by this power that the solar arrays generate. And also, one key thing that is powered by the power and propulsion element is the solar electric propulsion system. So just to give you a little bit of information about the solar electric propulsion system, when a spacecraft is in orbit, it's in an orbit, but orbits naturally drift. So in order to maintain the orbital positions, we have to do what are called propulsive maneuvers or orbital maneuvers to get the spacecraft back on track. And that requires fuel, and that fuel has mass. And so we're always focused on keeping the mass as low as possible. So the solar electric propulsion system actually uses the solar arrays to collect energy, and through some chemical processes, it ionizes a xenon gas, and actually allows that ionized gas to exit the thrusters that actually control those propulsive maneuvers. It kind of gives them a kick because they get excited and exit the thrusters with some extra velocity so that they can get back on track. And because of that, it's able to reduce the mass of the propulsive fluid that needs to be carried by up to 90%. So that's a big savings in mass. So that's why that solar electric propulsion system is so important. Basically convert solar power into thruster power. And that's, super important in terms of keeping costs down, risk down. So that's kind of why we love that technology. So obviously, if we're using solar arrays, we need solar power from the sun. So solar eclipses are also a concern for our orbiting spacecraft. And I want to talk to you a little bit about solar eclipses and lunar eclipses. Have any of you ever paid attention or noticed lunar eclipses as they happen? Oh, that's awesome. So good to see that. Okay. I'm going to tell you a little bit about the difference between a solar eclipse and a lunar eclipse, and you tell me if I got this right, okay? Thanks. Just a little joke, but we don't want to get really close to the sun. That's going to be an apocalyptic kind of event. But to be more serious, this is what we're all kind of gathered here together, for this big event for this total solar eclipse. So talk a little bit about that. I heard a video when I came in talking about explaining that solar eclipse is when the moon is covering the sun. We see those in the daytime, and it's during the new moon phase. It's, a very small kind of shadow that's cast in what we see here labeled as the umbra. And it's definitely unsafe to look at with your bare eyes. So I hope everybody's getting their glasses. So we don't want to hear about anybody getting their vision damaged from looking at the solar eclipse directly. So if you don't have glasses, ask somebody for them. And obviously it's only visible within that narrow path. And everybody here, we're really lucky to be in that narrow path. So excited to see it on Monday. And I hope that the weather cooperates with us to see it. Now, talk a little bit about a lunar eclipse. These are what people call blood moons. That's what I see them called a lot these days. So a lunar eclipse is a little different from a solar eclipse. But if we were on the moon, a lunar eclipse, what we call a lunar eclipse, would actually be a solar eclipse because it's when the moon is in the Earth's shadow. So the Earth has come between the moon and the sun. So it's all perspective, but we call it a lunar eclipse from Earth. That we see that at night during the full moon phase. Lasts up to 2 hours, between an hour and a half and 2 hours. We can look at it directly, and they're really pretty. There was one just on March 25th, and we see the moon looking red. And the reason is because of the Earth blocking the sun. It blocks the certain pieces of the electromagnetic spectrum. So the ones that show the purples and violets and blues are really blocked, the greens. And what we have left is kind of the oranges and reds, and that's what we end up seeing casting that shadow on the moon. And these happen more frequently because you can see with the Earth being so much bigger than the moon, it's a lot easier for the Earth to block the sun's light from the moon than it is for the moon to block the sun's light onto the Earth. So that's a little bit of difference about those. But again, we're having to look out for these lunar eclipses with our kind of moon orbiting spacecraft so that we make sure that our solar arrays are able to get the power that they need, generate the power that they need for the spacecraft. So we basically have part of our mission design is eclipse avoidance. That's one of our priorities here. And so we have an orbit, and part of how we are able to avoid some of that is by selecting the proper orbit. Gateway's orbit, it's called near rectilinear halo orbit. It's a mouthful, so we call it NRHO. And I'm going to talk to you a little bit about how it's selected in order to avoid eclipses as much as possible. Obviously, the planets are, doing their own kind of choreography, and we don't control that, but we can try to leverage and take advantage of what we know about that in order to avoid long periods of eclipse. So again, the eclipse avoidance, it's a priority in mission design. Spacecraft, they can tolerate eclipses for up to a certain amount of time, but that's all based on their power and thermal capabilities. So if you think about it, we could design a spacecraft that could withstand eclipses for 5 hours or 10 hours or 20 hours, but that means we're going to need to have batteries that last for that long as well. And if we have, the more power that the batteries need, the bigger the batteries are. And that means more mass, and that means more maintenance, and that means replacement. So we have downstream consequences of not trying to minimize the occurrence of eclipse. So that's why we focus on that and pay attention to it. And that halo orbit where we see that the spacecraft goes close to the moon in some places and it's far away in other parts of its orbit, those are kind of desirable because they have around somewhere between 30 and 160 days with full view of the sun. So definitely looking at halo orbits as probably most advantageous. But even with that, we still have eclipses of up to nearly 3 hours possible. And that could be about 4 times a year. But if we really focus on mission planning, we can avoid that as much as possible. So that's kind of how the orbit was selected. And another part of selecting an orbit has to do with these libration points. So I don't know if anyone's ever heard of people talk about libration points or Lagrange points. And I think when I first started hearing people talk about that, I was confused about what they're talking about. But hopefully this is something I can help you to be able to understand and talk to other people about at another time. But libration points are basically like parking spots in space. So there's places where you can put an orbiting spacecraft where it won't drift as far out of its orbit as if you weren't in one of those places. So you usually talk about the 2 planets that are involved. So in this kind of paradigm, we're talking about Earth-Moon libration point. For something like the James Webb Space Telescope, that's in a Sun-Earth libration point. So that's in Sun-Earth L2. We call it SEL2. And for Earth-Moon libration points, we call them EM. So there's 5 of those in the Earth-Moon system. And when we really kind of look at them, EML1 and EML2 seem to be the most likely and the best ones for human exploration. So they're the closest to the moon. And so they're the most relevant to what we're looking at for these missions. And then even looking a little bit closer, EML2 looks even better mainly because it can support telerobotic locations on the far side of the moon. So if you guys remember that we always see the same face of the moon. And on the far side, it's cold and dark. And we want to know more about that, but it would be better to send a robot to explore it than to send people because we don't really know what's there. So in order to have robots exploring that side of the moon without crew there to support that, we need to be able to support that from far away. So that's kind of what this telerobotic operations is, where we can operate these robots from a distance. So L2 looks better for that. So we kind of narrow in on L2. So we've decided that we like halo orbit, we like L2, and kind of look at the things that were ruled out here. These low lunar orbits up here, they're circular or elliptical orbits that go close to the Earth's surface, so they give you easy access, but they're also kind of in the moon's gravity well, so it's hard to maintain your orbit position there, so it's going to take a lot of fuel there. We have distant retrograde orbits, which are similar to the low lunar orbits, except they're wider in diameter. So they're stable, but they're kind of far from the lunar surface. So astronauts would have to travel kind of far to get there. So that's why the halo orbits kind of were decided on as the best. They're fuel efficient. We have an easy access point to the lunar surface. They're in the deep space environment that give us a lot of opportunities to study the science that we're looking to study. We have constant view of the Earth. So that means we can always communicate with the Earth with our communication systems. And then again, easy access from the surface. So what you see here is kind of a near rectilinear halo orbit around the moon. But even with that, near rectilinear halo orbits, those are families of orbits. So we still have to look a little bit further. And we have our moon in the center there, an L2 and L1. And so we have a northern family of L2, and we have a southern family of L2. We have a northern family of L2 orbit, L1 orbits, and a southern family. So kind of still have to look closer at those to figure out what's going to be advantageous. And when it was all said and done, Gateway decided on this southern L2, southern EML2 NRHO family of orbits. And the one that's highlighted in white is the exact orbit that was chosen because it kind of took all of the concerns into consideration. And that's the one that was selected. So when we look at all of it put together, we can take a look at what this is going to look like. So these are some visualizations, animations of Gateway, the moon, and the Earth, and the orbit. So on the left there, what we see is the Earth in the center. The moon is that green orbiting body that's orbiting the Earth. And then the purple is Gateway orbiting the moon. So it's kind of a lot to visualize in your head. So I love that they put this into a nice visualization for us to see. In the center, that's the same thing, but it's how we view it from Earth. So we see the Earth, the moon in green, and Gateway in purple, and that's kind of what that orbit looks like. And then if we took that and turned it on its side, and we'd still be looking from the Earth, that's what we see on the right here. So, this shows that there's a little drift every time it goes around, and we'll use our solar electric propulsion system to get back on track. And I think I probably shared a lot of information, and I hope it was helpful and useful. But just to kind of wrap it all up, I'll just kind of go through it real quickly. So give you a reminder of what we talked about, and then hopefully we'll have a few minutes for questions, and that'll be it. So just want to start by saying again that Gateway, it's a moon orbiting Artemis platform. We'll do science. We'll have crew there as an outpost so that they can get down to the lunar surface. My team at Deep Space Logistics, we are evolving the deep space supply chain. So trying to make sure that we can get cargo from multiple locations on Earth to multiple locations near and around the moon, the lunar surface. And then we hope that at some point we'll be delivering cargo to the moon, to Mars. We have our early Gateway science is going to be focused on radiation in the sun. Gateway is powered by solar energy, so that's kind of how we get the power for Gateway. We have a solar electric propulsion system that converts solar energy into thruster power, and that's how we keep our spacecraft on track. We have to worry about avoiding eclipses in orbit because we want to make sure that we have access to power our system. And we talked about the differences between solar and lunar eclipses, Earth-Moon libration points and what those are, different types of lunar orbits. And then we talked about gateways, NRHO, walk around the moon. And with that, that summed it up. So thank you.
Thanks so much, Bianca. That was fantastic. And we do have a few minutes for questions. So who has some really good ones? I see that our campers over here have some fantastic ones. Why don't we start over here first?
How many years does it take for an eclipse to happen?
How many years?
How many years does it take for an eclipse to happen?
Well, that is, it happens a lot. Well, I guess it happens enough, but like a total solar eclipse like we're experiencing this year, the last one was in 2017, at least here in the States. And the next one will be here in the States in 2044. So it's not that it's not really cyclical in that way. It depends on a lot of different factors. So there is obviously the orbits, but then we have the different angles of the planets that they're orbiting. So that's what I know, is that the next one will be here in the United States in 2044. So you'll be a grown-up then. the next time there's an eclipse here.
Yeah, it kind of depends where we are. There are eclipses that happen a lot of times, but the only place you can see them is in the middle of the ocean. But this time we're lucky that it's happening right here in Buffalo. You got one?
How long does the orbit take?
The gateway orbit?
Yeah.
It's a week.
Why don't we go over to this side? How about you?
Will there ever be lunar power, like you take the light that is reflected off the moon to turn into power?
Well, I mean, I think there could be, but that light a lot of the light that's reflected, that's directed at the moon is absorbed. So we're losing a lot of the power. So I think we could harness some power, but it's obviously it's more efficient to get it straight from the sun. But I mean, I like that idea.
Do you know any other planets that are like out of are like in other parts of the Milky Way?
Other planets, I think, not really. I don't.
We like our planets that are close to us, right?
Yeah.
That's enough.
I mean, I know they do study what they call exoplanets. So those are planets outside of our solar system. And dwarf planets. Yeah, so I thought about dwarf planets too, but yeah, and I don't really know of any offhand, but a good question.
Why do the moon go around the Earth?
Why is what around there?
The moon.
Why does it go around the Earth? The moon it's a Earth satellite. So the moon, kind of like how we orbit around the sun, it's like that's the center of our solar system. We're kind of the center of the Earth system. I mean, well, the Earth is in the same solar system, but it still orbits around us. So we're kind of like its center point to orbit around. Good question.
Did you forget your question? That happens sometimes. You remember? Oh, she forgot again. Tell you what, if you remember your question, raise your hand nice and high. I'll come back to you, okay? Oh, she's already remembered.
Where can I buy a solar array?
Where can,
Where can I buy a solar array?
Uh,
Excellent question, right?
I mean, telemarketers call me trying to sell me solar arrays a lot.
Calling you about your solar arrays extended warranty, right?
Exactly. Yeah, I mean, there are lots of companies that manufacture them and they want to sell them. So they're looking for people like you.
Google it. I'm sure it's out there. You can buy anything online.
Are there any other planets that have experienced eclipses?
Good one.
Yeah. I mean, other planets, anytime a planet another body gets in between a planet and the sun, it experiences an eclipse. We pay attention to the eclipses that we experience on Earth more so than any others, but that's a consideration in Mars exploration, just figuring out when there would be eclipse times because it's going to be cold. And depending on the size of the orbit that the planet goes in, the eclipse could last for longer. And so it's a really important part of any kind of exploration mission design.
What makes the sun rise?
What makes the sun? Well, the sun, we're actually rising. We're orbiting the sun. So it's kind of like the way that it looks to us is like the sun is doing the rising, but we're kind of doing more of the rising. And that's kind of just the way the universe is designed. That's what we kind of look to study is how did things start? How did this universe begin? So that's like a big kind of purpose of why we explore and why we try to look back into time and the development of the universe.
All right, we'll do 2 more questions. Let's go right here.
Why look at the ISS, may I ask?
Why look at it? What was the question again? Say it again.
why do you look at the ISS for ideas instead of coming up with better ideas besides the ISS?
I mean, that's a good question. So we look at the ISS because we've learned so much from the ISS, but some of what we learned from the ISS, we learn that it's not a good way to do things. And some of what we learn is that this is a great way to do things. So it's just an example that we can take and build off of. But we try not to be limited by just doing things the way that they've always been done, because then we'll miss out on opportunities to learn new ways to do things, better ways. So yeah, you have a good way of thinking about things.
All right, last question. Let's go in here a little bit. And why don't we go with you?
Why do you do it in that shape if only a little bit of about a time is around the moon?
Why do you do it in that shape if it's only around the moon for a little bit of time? Is that what you're asking?
Would you mean that it's only close to the moon? Well, because it's stable. The orbit is more stable. So the ones where we have the Earth, where the entire orbit is close to the moon's gravity pushes the spacecraft out of its orbit. So then we'd have to use more fuel to maintain the position that we want to maintain. So this gives us an opportunity to get close to it sometimes so we can have access to the surface sometimes, but it's also far enough away from it sometimes that it's not always being pulled, to the center of the moon like gravity does. To get to the surface? So they plan a mission when they're on the gateway. I'm just going to go back. When they're on the gateway, the gateway that we saw orbiting, so they'll be orbiting here, and the astronauts will have come on the Orion capsule, and this human landing system will be docked there. So what they're going to do is kind of plan, when does this human landing system need to undock so that they can actually drop down to the surface. So that's how they plan their surface mission, is based on when they'll have access. So it's all very precise, and they can't just do it anytime. They have to do it at particular times within the orbit to make sure that they have everything that they need, like the fuel, and that they're able to actually land on the surface.
All right, that's about all the time we have. Thank you so much for your fantastic questions. Those were some
Thank
great
you.
ones. Thank you so much, Bianca, for joining us
Thank
today.
you.
Big round of applause. And thank you guys for joining us here at Eclipse-a-Palooza too. We have lots of great activities going on throughout the rest of the day. Make sure you check those out. And again, thanks for joining us. We'll see you soon. Wishing you clear skies on Monday. Blow those clouds away.